Hello, today I would like to demonstrate how to set up a CVD model in Ansys Fluent. This model is largely based on a tutorial from the Ansys Fluent page. So the model as shown here is basically a model where we have an inlet velocity gas velocity inlet at the top, containing a mixture of gases, and an outlet at the bottom here, and the reactions happen on the surface of the disk that you see here inside of the domain, basically. So basically, the first step to ensure that this works properly is we have to define the species model. We have to enable volumetric and wall surface reactions. And then apply the right mixture material, which we have to define as well. So for this, basically I had to set up a number of species, and including solid species like gallium arsenic, as well as the site species for AS and GA. So basically, if I open up here, you can actually see the setup where we have the selected species that are participating in the gas phase, and we also have the side species and the solid species that only appear on the disk itself. So the reactions are defined in the reactions panel here. So here we have the first reaction out of a total of 2 reactions, where Ash3 reacts with the site species for gallium, forming gallium arsenic species and hydrogen gas, and this is a wall surface reaction with a number of properties that we defined for it. And for the second reaction, likewise, we have game3 or TMGA, reacting with a site species, forming a solid species, another site species, and CH3 radicals. And we also have Arrhenius rates specified for this reaction. So basically we have 2 reactions in this setup. The mechanism is set to basically a wall surface with a specified site density. For example, for this case, we use the 1 e to the minus 8, and we can also define the initial site coverage. So basically, for each site species, how much of it, how much are they occupying? So here we set a fraction of 0.7 for the GA and 0.3 for the AS site species. So we also have to define the properties of the mixture and the properties of each species participating in the mixture. So we have here Ash3, and here are the properties that we've defined with kinetic theory being used for thermoconductivity and viscosity, as well as for the diffusivity, as well as these is TMGA or game3, where we have a number of other properties defined for this gaseous species, as well as methyl radical and hydrogen. Here are gallium and arsenic. These are both the solid species, where we also have made definitions about their properties, likewise for arsenic, and we also have the site species here where we have defined properties for each of them, matching the properties of the solid species adequately. So basically, this is the basics of the setup. There's a lot of things that we need to enter for each separate species, but yeah, once that is defined, we can hopefully utilize the model. So once we have all the mixture defined, all the reactions defined, which is the key part for this model, we can specify the boundary conditions as well. So here I specify the velocity inlet, and I'm using an input variable for my velocity inlet, with a specified temperature as well as the species. I've specified also a mass fraction for the two gaseous species entering the domain. Hydrogen is my last species here, so it's not shown. And basically, we also have an outlet, which is just an outlet pressure, and we also have a backflow species mass fraction based on some testing. The walls have specified temperatures, some of them at least, and basically we have a temperature specified for wall 1 here, and I can show what wall 1 is by clicking here. So wall 1 is right at the entrance where the gas entered the domain. Wall 4 is our disk, so I can show that here. So wall 4 is where the reactions are supposed to happen. So to make sure that the reactions happen at wall 4, we have to basically specify a reaction, link the reaction mechanism 1, and we've also specified a wall temperature for that surface. Another important thing is this disk is moving at a certain angular speed, so we've specified an angular speed as an input parameter as well, with a rotation axis direction at on the z-axis, basically. So it's a rotational motion that we've defined as a moving wall. So if I go into the bottom here, we can visualize what the input parameters are. So my angular velocity for this simulation is 80 radians per second. My ash mass fraction and TMGA, or game 3 mass fraction, are 0.4 and 0.15. And velocity inlet for the gas is 0.01, and the wall temperature is 1023 Kelvin. So I've already run the simulation, so we can visualize some of the results. Here you can see the deposition rate of AS. So basically what we have is a higher deposition rate at the center, and it kind of fades away as you move towards the edges. We can also visualize the same for GA, so very similar profile here. We can visualize the temperature profile. So the temperature profile here on a cross section of the domain, basically of the cylindrical domain. So basically what we see is a higher temperature near the near disk, which is at set as a high temperature, as we've defined in the input parameters here. We can also look at game 3, or TMGA. So basically we have a higher concentration of TMGA at the center, and it kind of decreases as you go outward from the disk, and that might explain why we have a higher deposition rate near the center of the disk as well, as we have seen. So this simulation allows us to basically analyze the deposition rate on a CVD device. So we can do a lot of different customizations to this model. We could include a user-defined function to, for example, if you want to specify a different kinetics for reaction, we can do that by basically hooking up a UDF to my case file, to my simulation. So compiling a UDF and then linking that, and that would basically control the rate of my reactions. So I can actually have a UDF that controls the rates for the two reactions here. So that allows us a lot of flexibility if you want to use a more complex kinetics with more detailed chemistry and physics involved. Another way to customize a simulation is by using PyFluent. PyFluent allows you to basically automate a lot of the processes involved in setting up a simulation and running a simulation and conducting parametric studies. So this is an example of PyAnsys, PyFluent code that we could use to basically deploy a parametric studies using the same model that I've shown before. So what we have here is first we import necessary libraries for the model, the PyFluent libraries with all the prerequisites that are needed to basically run our model and do post-processing as well. So here I've defined arrays for things like the input parameters that we are looking at that we can vary. We can vary actually more of them, but I've included only 3 parameters: the gas velocity, the rotational velocity of the disk, and the temperature of the disk as well. So basically these are going to modify the input parameters using this expression here. So basically I'm defined a variable for each input expression, each named expression in Fluent, and these named expressions are going to basically take up the values of the variables that are there are from the different arrays, the different NumPy arrays, and that will allow me to basically modify each input parameter, each named basically each input parameter separately. Then I basically load a previous model already that I had run before, and then I basically use that as my initialization point with new modified input parameters, and then I run that for say 500 iterations as an example. And afterwards I'm able to calculate and run the calculations for 500 iterations. I can also control the criteria for continuity. Here is set to 1 to the minus 5. And then here is where we do a lot of the post-processing, basically generating some of the contour plots of the disk for the GA deposition rate. We can also generate data files as well if you want to do more post-processing within the Python environment. So there's a lot of flexibility, a lot of things that could be done here. This is just a sample code showing some of these capabilities. Afterwards, you can save your case and data file separately, and if you would need to ever rerun again, you can basically use this as a starting point. So this is basically it. Thank you and have a nice day.